So far I tried to cover some what I expect to be authentic materials, and I would like to acknowledge that they have been taken from the respective manufacturer's catalog, retrieved in around this time when this is recorded. That must have been in October 2017, and again I leave it to you as things progress, that you need to take a call and have a look at the latest thing. Now I want you to look at something which I have taken from my our lab. See here, this is typically the classroom where they are being recorded. So I have this touch PC here, tablet PC, then I have this pen, and then I need to bring all these small items to have them recorded here. So a typical recording session, probably it's a little more cluttered, and then we try to show things. Now I will take you directly to the lab. You see here, it's a small like you have shop in a mall. It's one of my colleagues' genuine desk. The computer is on the right side, and then he has a small table. On this is typically where everything starts. I have no choice. Motors, back to back, auto transformer, you have power supplies, you have a huge isolating transformer, and then you have all this, and this has been brought from there. And in the initial stages, we don't use too much of instrumentation, as much as use one of these simple coolers which you are likely to find in your kitchen. This is probably a meat thermometer, and but this is good enough because the overall mass is low. Next picture shows you things a little closer. This is what I tried to show you yesterday, that a small isothermal block. From various practical purposes, we need to create an aluminum block. Whole thing is driven by, you see here, this power supply is SIM critical. So we still have a problem in case you want to use any peltier. We end up with three things. One of them is you need a power supply to control the current through this device. Another is a way of monitoring the temperature, and then you need probably active control. Otherwise, it has a tendency to stay grounded. So these are the two flame light tech. These two things have been put. They have been kept underneath that block. And I have told you, the manufacturers generally give you some idea about which one to choose and so on. You have not much of choice from that. So there are two ways of it. In a mode like this, you can make them parallel. That is, you have more surface area to be contacted. I have intentionally kept it like that. Obviously, they are kept one next to each other. Alternatively, you can stack them and make them into a series module. So it is for you to play around. Now I will take you back to the actual lab, which has all these threatening electronics here. You see, that is how typically a power lab is likely to look. And except the student, for everybody else it's a booby trap. Better not touch. If you touch, they have to get a new professor. So I will get back to you. In the initial stage, this maze, or what looks like a rat's nest of all these things, is inevitable. And then I will try to take you closer. You see here, we have a small heat sink, and then you see here, this is all where the active devices and the capacitors are mounted. You have this DC link capacitors, then you have these permit me to use the word which I do not like, heat sinks. This is how it is. If somebody tells you, unless you happen to be working in a firm which has foreign collaboration, and somebody already sells you this equipment, the reality is this. Not long ago, we had this issue of saying, heat sinks need to be black. Two things I want to point out, I will ignore that heat sink black business. What I would like to tell you is, if you see these heat sinks which are narrowly spaced and they have one limb which is probably projects into the equipment, you can make out that it is naturally convected. It uses a natural convection. Anything which does not have this, we will end up with having to make things. I will go back here and I will show you. Have a look at these things from here. Can you see here, the first thing here? That is probably a bridge rectifier. So, and I am not sure what it is, my interest is only the heat sink part of it. Now, you see here, you see the very peculiar or very very characteristic way of putting all these fins and so on. At the moment, I will not comment on this, saying except that they have all been developed for specific purposes. Why it is like this, and whether there is a fan, whether 4 of them are to be stacked end to end and all this, that you need to figure out. And you see, we have something else at the back. You have seen here, that is that fat heat sink I have been carrying around, and for convenience sake they have mounted one on the available heat sink, there is something else which is mounted here. Now, I will try to ask you to recollect that one solar rack. There, if you see at the back, we had those blowers, and usually they probably see this back of this heat sink. You see here, it is very fat. Maybe the next picture is a little closer. Sorry, the next picture again. Yeah, you see here, this is very thick here to help in transient this thing, and also in the case of any failure of the fan and all that, the heat can be held for a short time, and then you have tapered heat sinks. So, these all have been made with a little bit of practice, then analytics, and then later on eventually optimized very carefully. Now, we come to these things saying what is the reason why somebody has made this. This is what I call your guesses as well as mine. You see, these are all various I think maybe gate drive circuits and all that, and you have this heat sink on which there is a PCB. Probably there are active components directly mounted on this. Okay. So, well, it is convenient for us to talk about concurrent thermal engineering or thermal management. Somewhere in the beginning somebody has to take a call and do these measurements. There is no equation which says if you have this much of a power dissipation, or this is a style of equipment, this is the heat sink naturally. It still is. While I will not call it trial and error, you still have to take an intelligent call on where to start. Later on the optimization comes. So, if you have some idea of the thickness of these wires, now you know what it is. Typically, something between 100 to 300 amps peak is being handled there, hence you have all these things here. That is the bottom of the diode which they are showing you, which the student. So, I would like to thank the student about the diode. It was probably removed after the failure. This is where I would like to point out what I had started in the beginning, saying the thermal conductivity of air is very poor. It is only marginally increased by applying this so called thermal paste. Still, thermal paste as such conductivity is not good. If you go back to the earlier lectures, in the appendix it is given there. So, coating it with a tremendous amount of this this material, or even there are conductive epoxies, is not a solution to proper grinding or lapping both the materials and attaching them together. And you have seen this, everything has its own polarity. And then one funny, I do not know whether they are visible now, they are plus and minus here, and something else is written here. There is some, one wiggly thing here, and there is a small offset. Probably it is a, and then I can faintly see a U. So, it is probably a 3-phase rectifier, I have no clue, but my interest is only to say that whenever there is a heat sink and at the that contact surface, usually best lapping has to be done, especially in production, especially things are very, very critical. Luckily in our case, students are observing only transient phenomena as such, it probably does not make sense. Otherwise, this surface has to be perfectly ground and lapped to meet the other surfaces. Okay. So, we can maybe get out of all this. Now, you come to practical things. You see this neat power supply here. At one level it looks fine, absolutely, and from the packaging point of view, it is just what is called an open chassis. By itself it is not intended to be used as it is, but if you can relate that recollect the solar racks which I have shown you yesterday, you will see these power supplies and all directly mounted inside the rack. The rack itself is a IP55 or depending on the environment, occasionally IP56 or IP65 type of a enclosure, and for convenience sake it comes with a small protection mesh. One or two things you will notice about it is that while it does not fully protect everything, but any accidental drops of tools or wires or anything, it will not short circuit the PCB or leave them in a damaged condition. So, some physical impacts and all we can avoid. Now, I will see if I can open this and see how it is treated. So, the next picture that has been brought and kept on a table, you see here. One thing you will notice is we have some L shaped some mounting plate, and my rather our student is helping me open the thing. He believes in me, he knows very well that I am not likely to damage it. You have seen that they are just 4 screws, and when you lift it out, we have this beauty. I am sure you will appreciate what it is that the whole thing is. So, at this corner you can see, can you see here? We have 2 active devices directly mounted on a small aluminum sheet, which is all the main purposes of the heat sink, and the fact that its whole thing is open and it probably in a air stream inside another cabinet, this is sufficient, absolutely sufficient. Same it is here. See here there are 2 more devices here, and then I am not very sure why it has been bent and brought here. Same thing here, you have many more devices here, and just like that hot coffee spilling on your thing, you see here, this is not about heat, this is about the rail being charged. It could be one of them could be a positive rail, another could be a negative rail. As such, these are the small heat spreaders we use in equipment like this. So, I thought I will stop there, and then I will try to come back to an interesting. Some of you may have heard that the latest June 13th it has been written about Xbox One X. It talks about liquid cooled Xbox One X due to in part to the marketing blitz by Microsoft on stage during the briefing. Although the term liquid cooled may be technically accurate, the terminology can be confusing and extremely misleading. Liquid cooled does not mean the same thing as a liquid cooled heat sink or anything. It is not a liquid cooled in a traditional sense. When you think of something as being liquid cooled, The average person pictures an all-in-one cooler or an enthusiast water cooling loop with a water block radiator and pump. The form of cooling is the preferred method of heat removal for highly overclocked processors and GPUs that generate enormous amounts of heat. That is not what is being used in the Xbox One. Instead, it uses a vapor chamber. The type of cooler has been used for more than a decade to cool something high end graphic cards and so on. So, I will now stop it here, go back to the next this thing, in which see what happens in a vapor chamber thing is, at the right side you have a heat source, then this thing is filled with some liquid which starts boiling or phase changes, and that latent heat carries away the heat. That latent heat now makes it condense on another surface, usually directly above, and then the water is the liquid gets removed. Vapor chamber heat spreaders are planar heat pipes that spread heat from concentrated sources to a large area heat sink. The effective thermal conductivity is greatly exceeding copper. So, you can read it for yourself with me. We have all these things. Those people developed a chamber made of a copper plated ceramic casing close to silicon. This allows direct bonding of semiconductor chips to the vapor chamber. Direct soldering of the chips to the chamber reduces thermal interface resistance and eliminates need for mechanical clamping. Chips can be placed anywhere in the vapor chamber surface. Heat sink locations can be flexible. The condenser can be at the sides of a typical, as is typical for liquid cooling, or over the entire vapor chamber and so on. So, low thermal resistance achieved independent of vapor chamber heat sink location. So, we have here, if you see what you call the type of heat flux, it is 100 watts per centimeter square, 300 watts centimeter square and so on. So, 500 watts per square centimeter in heat flux, lower than 0 in evaporator thermal resistance and lower than 0.12 in overall vapor chamber thermal resistance. So, my suggestion is you have a look at it. I am just showing you. So, it is very much convenient for you to have a look at it. Now, I will see if I can play something which I fully like to acknowledge from these manufacturers. Have a look at this. So, that probably about sums up what is a vapor chamber heat sink. Now, advanced cooling has a similar this thing. This is slightly same thing once again, it is almost like an animation, and it is expected to run again and again. You see here it is getting That is all there is to it.
Sapphire was the first major PC component manufacturer to card coolers use heat pipe technology structure that contains a working fluid that changes from liquid to gas when heat is applied anywhere on its surface.
What is a vapor chamber heatsink? A vapor chamber heatsink is a much better way of cooling something rather than using a heat pipe. You'll find this type of heatsink in much more higher end graphics cards such as the GTX 1080 and 1080 Ti. The new Xbox Scorpio should include this type of cooling method. This is how it'll work. The vaporized coolants convex freely through the chamber. The molecules then condense on cold surfaces, dissipate their heat load, and are channeled back to the coolant reservoir. Since the rates of condensation depends on the temperature delta of the coolant and the contact surface, the coolant automatically streams towards the coolest surface area. The coolant stream within the vapor chamber is responsible for its superior thermal properties. As a result, it provides stable and evenly spread temperatures on all of its surfaces, regardless of the location and density of the heat source below the chamber base. And that's how a vapor chamber heatsink of its surfaces, regardless of the location and density of the heat source below the chamber base.
So, now getting back, you will notice that if we are to use a simple heat pipe and so on, we have this little problem still of if you have a hot spot and if you have multiple heat pipes, you still have this problem of some of them getting a little hotter compared to the other thing. Compared to that, if you have a vapor chamber, the thing can be equalized. So, it is for you to take a call and what do you call, wonder now what to call what. So, I will close this. Now, I will come back to this again. This is slightly what do you call a longer thing. Listen to him.
Know that there was another cooler I needed to buy. This is the ID Cooling VC45, and this is kind of a unique cooler, even though it looks very much like the Noctua NH-L9i, because it features a vapor chamber built in. So what's it like? Let's go find out. One thing. So the last video, I purposely chose a CPU that's too hot for the Extra Mini. The second thing, which is really important, is that I was using version 28.9 of Prime 95, which is what I use for all of my stress testing CPUs. But what it does do very well is generate a lot of heat, which is why I used it to compare these coolers. I want to thank Dr. Zaber from the Century Project for asking me to clarify this if I did any more future heat testing videos. I'm also going to use version 26.6 of Prime 95 in this current benchmark to show you a more accurate stress test that is safe for the CPU, at least more safe. So with this disclaimer out of the way, let's go blow up my CPU. Your job is to stop it from blowing up. Presentation is, well, it's packed well. Not much for presentation. Comes with everything that you need to actually cool your CPU down, which is, in the end, what you pay for. Also, some weird plastic fibers. Box is kind of boring, but then again, so are my S4 mini boxes, and who really cares? It's about the coolers. To do any test, I'm going to have to remove the Noctua from my current test motherboard, which is super easy. 4 thumb screws, that's all there is to it. So the VC45 does come with a thermal interfacing compound, but I'm not going to use it because I want to be consistent with my heatsink tests. So I'm using Noctua's NTH1, which is what I use in all my builds. It's good stuff. It works really well. I put a pea-size amount. This is what it looks like. This is a pea-size amount. The mating surface of the VC45 is awful as far as finish. Surface of the VC45 is...
This is probably what was that small device attached to the fan which I brought you yesterday. I need to drill out the core and see whether there is any liquid or anything, but you will notice here that this is slightly different from the conventional simple heat sink with a copper core and something which is spread on top of it. Now listen to this fully.
Awful as far as finish. I mean, it's one of the roughest surfaces I've seen in a cooler. I don't think it matters too much, but if you were expecting something lapped and polished, it's not here. The VC45 does have an adjustable mounting system, which is really nice because you can install on more than one type of motherboard, but it does make it a little trickier to install. You can definitely over tighten it though, so make sure you don't warp your motherboard, and just tighten it as much as it needs to be, but not anymore. Installing the clips for the fan was really difficult. I mean, I had to look at the instructions, that's how bad it was. And the instructions actually showed a different style clip, so I was even more confused. But at the end of the day, I finally figured it out and broke in the fan clips. And I didn't shoot my eye out, so there's that. And it's all bolted up and ready for some testing. Okay, round one's pretty boring. Stock voltages, stock clock rate. Noctua's a little bit cooler, just a little bit. Running version 26.6 Prime 95. And yeah, the Noctua's actually, during this cycle, cooling a little bit more CPU. So I guess the winner would be the Noctua, but still too boring of a test, so I've overclocked the processor to 4.5 gigahertz. This is, of course, the VC45, and I'm running the hot version of Prime 95, the deadly version. And yeah, it was pretty hot. It eventually did throttle, like after 10 minutes. So I put it back down on the 26.6 version with an overclocked CPU, and it throttled, but after like 15 minutes. So I guess, well, obviously the CPU is not for overclocking. So here's the thing about the VC45. It's pretty loud. It's louder than Noctua, but listen for yourself. Let's test it against the Noctua fan. Now I'm going to need a beer to wrangle off this clip. Okay, so I have the Noctua fan on the VC45. Let's see what she does. About the same, actually. I was actually surprised to not see much of a difference. Except for noise. It's a lot quieter. And I made good contact with the VC45, so I know that wasn't the issue. Both on the CPU and the backside. Done a couple runs, but here's the last one. It's a confirmation run, stock voltages, and looks like the Noctua is a little bit cooler still, by just a teeny tiny bit. But it is quieter, so I think it has to do with the fan, because the heatsink design is pretty similar. The Noctua has more fins and a heat pipe, but I guess that offsets any advantage that the vapor chamber has on the VC45. Well, that was, pretty close. Almost too close to call if we're talking about just the temperature data. But that's only if we're looking at the raw temperatures. Because there's a lot of things about this cooler that I just don't think holds up to the NHL9i. So is this a bad cooler? Absolutely not. It just can't dethrone the king. But maybe with an update and some heat pipes, it could. Or with a much lower price tag, I would definitely be tempted to go with this cooler. But because, at least in America, it's more expensive than the Noctua, it's noisier than the Noctua, it's not as pretty as the Noctua, I would have to go with the Noctua. Thanks for watching this video. Give me a thumbs up or a hate comment if you hated it. And frankly, I probably deserved it for being negative about a product on the internet. Whatever you do, hope to see you next time.
So, coming back, you need to probably verify what is being published, and the thing is, unless you are an OEM manufacturer or a very serious person or a what do you call a researcher, it is not possible for us to attempt fabricating any of these things, especially these vapor chambers and all. They are all made specifically for a chipset. Imagine let us say you have a 30 mm by 30 mm external surface on which you can bond this, then along with the cooler this makes a neat package. There is not something you attempt to make on your own in your lab or anything. Same thing a little with your heat pipes also. Heat pipes, it is all well known, but if you have something ready made, you can try to use in your other things. So, by default we still end up with simple conduction, and how to improve the conductivity between whatever device is being cooled onto a heat spreader, we loosely call a heat sink, and then with the available what you call space and geometry, how well you can make a heat sink. Try to use one, or you can make one also, and then use all your what you call creative techniques to see how well you can arrange these things on a printed circuit board, because the whole package just needs to be small, and then eventually this is at the smallest level, then in the equipment level one way of dealing it, and then finally we come to the racks, and in fact you have a large installation, you are forced to take all the heat out from the larger rack. I think I will pause here for a while, and I want you to go back to all the that wherever the position this video has been recorded, read up a little more about the practicality of each of these solutions. That is the reason you do not find these things very what do you call widely used in your equipment. So, because they continue to be still a little bit of novelty and very conventional way of selecting a heat sink and then using some way of convective cooling, this will help. However, to make this little what do you call complete, I will take you to old Remsburg book, in which a whole chapter has been what do you call. If you go to the second part of this whole book, a huge amount of what do you call data has been presented, and an analysis is presented here about phase change. See, it is relatively complex, saying heat transfer of a phase change coolant is much more complex than the previous modes of heat transfer. By phase change, we denote liquid changing to a vapor, evaporation, vapor changing back to a liquid, condensation, then solid changing to a liquid, liquid changing to a solid, solid changing to vapor, sublimation, and vapor changing to a solid, deposition. So, these things, this what you call textbook gives a huge amount of definitions of what is vapor pressure, above absolute 0, molecules in a liquid are in constant motion. Some of these will have a higher velocity than the average. The energy is one of these high speed molecules greater than the coercive forces, molecule can escape. This is evaporation. If the liquid is in an airtight enclosure, the escaped molecules will fill the airspace. Some escaped molecules will even re-enter the liquid. Eventually, the number of molecules escaping equals the number of molecules re-entering. We call the airspace as saturated vapor. So, here we need to remember two things. One of them is, if you leave something outside in the open, it has a tendency to evaporate at a slow rate, which is very different from boiling. In boiling, because of the amount of input giving and actually phase change occurs. So, both of them there is latent heat involved in it, the rate of change is the issue. So, typically, let me get back to your old high school physics. You have an empty pond. Sometimes you will notice that the pond appears a little cool, too cold in the morning. The same pond some other times does not appear so cold. So, the standard explanation that is given there is, one is the evaporation at the surface, the other is the universe is a big black body. On a cloudless night, all this water loses heat directly to the universe which is dark. If you do not have any, what do you call the stuff about ambient lighting, and hopefully stars, of course, star gives light, not much of heat, and you do not have any of these sources, things become extremely cold. So, you have evaporation plus radiation. Now, down the thing talks about what is phase change. In the previous discussion, the liquid molecule change phase from a liquid to vapor. If the walls of the enclosure from previous are suddenly cooled, we would again supersaturate the vapor. So, I would like to draw your attention to very common things which we see. If you were to take a hot cup, teacup, place it on a horizontal surface like your what you call table or workbench, you will notice that after a while when you take it off, it forms a small patch there, and you can see condensate on the patch. In contrast, if you take a bottle having some, let us say, cold liquid or a glass of cold water, you will see that there is condensate all around the outside surface. The issue there is this saturated, super saturated this thing for a given temperature. So, if you have a cold surface, in the case of our teacup example, the horizontal surface was cold, the cup itself is warm. So, it condenses on the colder surface. In the case of a our what you call tumbler with some cold liquid, it is cooler than the ambient. So, it will condense on the walls. So, a lot of it explains what are the phase diagrams and so on. Probably you have seen this here. So, I suggest you spend a little more time unlike me, and my talking about it. So, at a given temperature, what is the which part of it is liquid, which part of it is solid, which part of it is gas, and which is a vapor. This is the diagram for water. So, we all know ice depending on the pressure, we all know which is the liquid phase, and we all know which is the vapor phase. So, as you compress the liquid or as you compress the gas, how does it behave? As you evacuate the gas, how does it behave? The operation or choice of operation on this is where both your refrigeration, air conditioning equipment as well as our vapor phase coolers will work. Depending on when you want it to boil, when you want it to what do you call cool, and then what is the pressure at which these things happen, you have a closer look at it. Later on, it is whole thing is explained in the text. Phase diagram for this thing, A is the triple point, B is the critical point, curve AB shows the point at which water can exist in both liquid and vapor phase. So, you have seen this A and B is where we work with in all our this thing. So, depending on the what you call amount of pressure you apply, how much of gas you fill and all that, standard atmospheric pressure is 760 what you call torrs or 760 millimeters, which is equivalent to something. Moving along the torr line, we see that H2O has a phase change from solid to liquid at 0 degrees centigrade at standard things, changes from liquid to gas at 100 degrees centigrade. Typically, this is used in your milk boilers. So, if you take a milk boiler, it is nothing but a water jacketed vessel left to the atmosphere. So, I will see if I can go to the internet and look for a milk boiler. I am sure some of you have seen this device. Madam, show me this this thing. This is typically a milk boiler. We know we have this serious problem with the milk this thing. If you keep milk on any what you call hot plate, stove, gas or anything, first thing is as long as you keep looking at it, nothing will happen. Even momentarily you look away and then it will boils over. So, is there a way of avoiding it? So, what generally people do is put it in this water jacketed vessel, which is called a milk boiler. So, there is nothing outside, there is a small opening here, you fill it with water and then you keep it on your hob or gas or anything. As long as this is getting heated up and even when it is boiling, especially at a low temperature, it will keep condensing on the inner jacket. You have an outer jacket and an inner jacket. The liquid from the outer keeps condensing on the inner jacket, or if they are directly in contact, it will not boil, which is the beauty of it. Usually this is filled probably about between 1/3 and half the way. So, the advantage is as long as you are heating it by conduction, and if the milk inside is still in the normal condition, you will notice that it will not boil over. And the moment this boiling will start is probably when inside temperature is approximately reached a few degrees below the ambient boiling point. And one more important thing is it must be left open to the atmosphere. Then the moment this boiling starts, there is a whistle attached to it. So, the whistle whistles and you take out, and so we have any of these beautiful milk boilers. Main principle is milk boiler is it's simple water jacketed vessel. You have an inside container and then you have this outside container. You see here you have a lid and it is a double walled thing where the container is filled with water. This is all there is to it. Any of the vapor chamber coolers which you are talking about. Why I keep giving you these common examples is that you may not be working in a lab. Besides, you can always make an experiment. So, we will notice that H2 has a phase change from solid to liquid at 0 degrees centigrade and changes from liquid to gas at 100 degrees and so on and so on. So, this is typically what will happen even inside your so called vapor chamber what you call devices. So, as an object absorbs energy, the object will display a temperature increase defined by the specific heat of the object. We call this temperature increase sensible heat. Another form of heat is latent heat, by which the object will absorb energy but will not increase in temperature. That latent heat of vaporization is higher than the latent heat of fusion, because the molecules are spaced so on and all. The advantage is in boiling until the last drop of liquid gets evaporated, the temperature does not change, which is exactly what is the principle used in the water jacketed vessel. And it looks like milk and then with that little temperature drop across the container will never boil over in that water boiler which I was milk boiler which I was showing you. I will leave you here for you to talk about this Jacob number and so on and so on. So, thank you. I will just stop here, okay, and I will continue with the theory in the next class which I have. This is probably I already covered a little time. So, thank you.